kind of started last time. One of the someone was talking about how on earth do you put in the domain of a function, or the values where a function is continuous. And essentially, you don't need to do the curly brackets. All you do is you write down the x squared plus y squared greater than 4, something like that. So I'll show you that when we come to it. I've just realized there's one question that I want to show you the working for, and then I'll go and look at the homework. And that is a guy called squeeze theorem. And it's question 10. I believe it's the only one that asks you to use this technique. So we are going to find the limit as xy tends to the origin, 0, 0. And the function that we're going to do it with is xy, the sine of 1 over x squared plus y squared. Now, I could try and solve this one by doing the y equals mx technique. And I haven't tried it, but I'm pretty sure that it works. You'd have to do some L'Hopital and some really messy stuff, but I think it would work. But let's do essentially the squeeze theorem. So I'll show you how this is going to work. I don't know what the value of this is at any given, at all values, but something I can tell you for sure. Since it's a sine of something, would you agree that the sine function is guaranteed always to be between 1 and -1, regardless of what goes inside? So the sine of x cubed, the sine of x plus 1, don't matter. Because it's a sine, won't it be sandwiched between 1's as big as it's going to get and -1 is as small as it's going to get? So far, so good?
Didn't we do something exactly like this in the series?
I can't recollect. I'm not saying we didn't. I just can't recollect.
It was like we assumed sines and cosines would always be 1 or -1.
Well, maybe. You've got a better memory than me. What I'm going to do now is multiply all of them by xy. And the reason I'm doing that is I want to have this guy in the middle. So would the logic be that if this is true, won't this also be true? Right? Because I'm multiplying everybody by the same thing. Then shouldn't the limit as xy tends to 0, 0 of this guy also be true to do this information in terms of limits? God, it takes forever to write this thing down. Would you agree that the logic says that this is also valid? If sine is between -1 and 1, then negative xy, right, this fella here is somewhere between negative xy and plus xy. And so shouldn't the limit as x tends to 0, 0 be true? Now, what do I know about that guy? Would you agree that the limit of negative xy as x and y both become 0, would you agree that is 0? On this side, would you agree that it's also 0? And so what we're left with now is that this must be true. Wait a minute. Isn't the only logical conclusion is that if this is between 0 and 0, that this must be 0? And that's us proved the limit is 0 using the squeeze theorem. Are we cool with the logic of that? How we could come up with a limit by just sandwiching it and then finding the limits of the outside pieces of bread. And if each piece is 0, right, then the guy in the middle's stuck. It has to be 0. It's the only way that's going to happen. Right, now let's look at when a multivariate function is continuous. Okay, make it a little bit bigger, hopefully. Now, here is a function, fractional function. When is this function continuous? It's the same thing as when is what's its domain, right? When I look at this, I look at the bottom and I say, okay, if there's going to be a problem, isn't it going to be when the bottom is 0? I don't really care what happens to the top of a fraction. Typically, it doesn't cause any damage. But you don't want a fraction with 0 on the bottom. But the way I'm looking at that is, can 2 plus e to the power of anything, whether it's x minus y or not, doesn't matter. Can 2 plus e to the power of something ever be 0? And the answer is no. E to the power of something is always a positive number. So you're going to have 2 plus a positive number. It's never going to be 0. That means everybody is continuous for every single value. In other words, there isn't a problem. You can't pick an x and y, no matter how hard you try, and make that fraction horrible, right? It's always going to be a number that you can get. Now, this guy here has a problem because of the square root. And would you agree that this is only going to work as a real number when the thing inside the square root is greater than or equal to 0? Agreed? So I want 1 plus x minus y to be greater than or equal to 0. And one of these guys is the same thing as that, but just kind of rearranged. So if I have 1 plus x minus y greater than or equal to 0, isn't that the same thing as x minus y greater than or equal to -1? Isn't that y minus x? Oh, darn it, I'm saying too much. Nobody could understand what I just said. I have to write it. You have to just see it. Just too much going on. So, in the guy that we've got, it's the cosine of the square root of 1 plus x take away y. So I know that this has to be true. And I'm now going to rearrange this guy by subtracting 1 and subtracting x's. I'm then going to multiply everybody by 1, and I get that guy. And that happens to be, in my case, circle number 1. Are you comfortable about switching the order when you multiply an inequality by -1? Okay. It's probably easier, I think, if I just write them down then. So this is what question 13 would look like. And we have on the top, we have this guy. And on the bottom, we have this guy. Now this function is going to have a problem when the bottom is 0. Agreed? So how am I going to describe the domain? Well, it's going to be that fella. This is already given to you. If you rearrange this, isn't it the same thing as saying x squared plus y squared equals 2? Are you comfortable with that being 0 is the same as saying this is 2? If you want to see the in-between lines, I can put them in. But is it kind of obvious that 2 take away that's nothing, so this is 2. So I am looking for x squared plus y squared not being 2, right? As long as it's not 2, you're good to go. Okay, let me show you what that looks like now in the homework box. Here's a xy such that x squared plus y squared does not equal 2. You see, you basically just do that. Right. Now, next one, I'm going to go and write it down. I think that's going to be a little bit easier. I hope at least a little bit easier. Now, in this case, we have a function. So it's question 14. It's capital G of xy and it's the square root of x, and it's the square root of 4 take away x squared, take away y squared. Now, if this thing is going to work, that guy has to be greater than or equal to 0, right? That's one of the restrictions. Doesn't this also have to be greater than or equal to 0? Right. Now, if I rearrange this, it's that guy. In other words, 4 has to be bigger than that. Of course, we prefer the x squared to be on this side. So this is equivalent to that. You're comfortable that if 4 is bigger than that, then this is less than 4. It's just another way of saying that information. So what it will look like, and this is pre-built, right? So this is in the answer. You just put in your 2 restrictions. So you say that, comma, and that. And that would be your final answer. Let's see which one of them does that look like in my world. In that one, it's a third circle, but who knows what it is in your case. And this is a version of 15. Right, if you're going to be able to use this function, it's a log of this expression. For a log, doesn't the thing inside have to be greater than 0? Not greater than or equal to, but greater than 0. And all I'm going to do is rearrange this restriction so that it's got y in its own. So if you subtract x and 2 from both sides, you get that. And if you multiply everybody by -1, you get that. So that's the restriction I'm looking for. So you will look at your list and you will find the one that says that. And I believe in my case, it's the third circle. Right, that's relatively quick because I was hoping to get this over with efficiently. Are we cool with the process of continuous? Couldn't that question be what's the domain? It'd be the same answer, right? They're equivalent. So time to move on. And what's our next thing that we're going to deal with? Is kind of a biggie. We are going to look at partial differentiation. In fact, when you do, if you do Calc 4, when you do that guy, you are going to find out that we start exactly here. So there's going to be a little overlap in Calc 4. We are going to look at finding partial derivatives. What are partial derivatives then? Well, essentially, it's how you differentiate a multivariate function. But some of the rules have to change, and the notation certainly changes. I'm not quite sure where the heck we are. Let me double check. Right, we are in the whiteboard, okay? If I went and said to you, f of x equals x cubed plus 2x take away 1, and I asked you to find its derivative, you would do that and you wouldn't think anything about it, right? Finding derivatives is basically, in this case, the power rule. Now, we have different notation. Sometimes your function is called that, and its derivative would be that fella. And sometimes your function is this guy, and you would write down the derivative like that. I think we're comfortable with that. Are we not comfortable with the fact that when you did Calc 1, that there was more than one way of saying find a derivative, right? Do y by dx is the same thing as y dashed is the same thing as f dashed, right? Now, if it was f of t, wouldn't the derivative be that guy? Are we also comfortable that x and y are no more special than T, W, Z, P, and any other letter of the alphabet? As long as you have a function of a variable, you can find its derivative. So how does partial differentiation work? Well, it's got a major issue. There is an example of a multivariate function. Here's the first issue. When we were Calc 1, wasn't x the variable and y the dependent, right? So you knew who the variable was, it was x. And you could only differentiate on x's or p's. Can you see now that there are two variables? Each one is just as valid as a variable as the other, right? X squareds and y cubes, x's and y's are both variables. That means that when we say find a partial derivative, there are actually two of them. One is the derivative when you think of x as a variable and you treat the y, the other guy, as a constant. And the second one is you switch places. You do the derivative as if y was the variable and anything else is considered a constant. We have notation for it. We do that guy. Now, that's not me being funny. That is the shape of it. It's not a D like that. It's a Greek delta, right? You notice the notation. It's very specific. Now, what you have to do a partial derivative is that you got to have good imagination. You look at this function and you say to yourself, x is the variable. Any other letter of the alphabet, I am going to treat it as if it was the number 42, as if it was just a constant, right? So differentiate x squared with respect to x is 2x. What would you get if you differentiate the number 7? With respect to x? What would you get? You get 0. Now, be careful here. What would you get if you differentiate e to the power of y if you think of y as being just a number? It's like e to the power of 42. That's one of the things I do in my brain when I get confused. What's the derivative of e to the y with respect to x?
0 because it's a constant.
It's a constant. Now, the guy that's left is this fella. What do you get if you differentiate, partial derivative, I should say, if I'm being precise, xy cubed? What do you
Y
get?
cubed.
And now, nobody writes zeros down. Are we happy about how the partial differentiation process works? One thing is a variable, in this case x. Any other letter of the alphabet is treated as a constant, right? It's treated like a 42. Now, same function to start with. I'm just writing it down again because there's a lot of things in the way. You could also be asked to find the partial derivative df by dy. Now, there are 4 guys here. Let's see where they go. What is the derivative of x squared when you consider y as the variable? What's the derivative of x squared when y is the variable?
0.
Great. Would you agree 7 is 0? Now, what's the derivative of e to the power of y when you consider y as the variable?
E to the y.
And lastly, what would xy cubed be if y is the variable? What's the derivative?
3xy squared.
And then tidy up by ignoring the zeros. Have you noticed that those two partial derivatives are not the same? In fact, they don't even look vaguely similar even. You noticed? Does that kind of make sense that you would probably expect that to happen? That when you differentiate partial derivative with respect to, say, one variable x, it'd be very rare that you'd get the same answer if you did it with y, right? Because things, disappear differently for starters. Are we cool with this process? It's really just calculus in the differentiation, but now we need the imagination of being able to look at a letter and pretending that it's not a variable at all, it's just a number, it's just a constant. We'll try this fella. Now, there is the notation for the partial derivative of f with respect to x, but it is also has this notation, which I actually kind of like. It's an f with a little baby subscript x. It means the same thing as this. I know why I like that notation. I think it's just elegant, right? Just me. Now we're going to go through each one of these guys and differentiate it with respect to x. Okay, so we'll start with the first one. You should probably do colors. Then I'll do the second, and then we'll do the third, right? What do you get if you differentiate x cubed y squared with respect to x and consider all other things as constants? X cubed y squared, what do you get?
3y squared x squared.
Okay. Now I'm going to deliberately do a mistake here. I'm going to differentiate the sine of xy, and there's going to be something wrong. It's going to be half right, but also half wrong. Oh, if you want to differentiate the sine of xy, you get the cosine of xy.
But it's a chain rule, so you got to multiply it by the constant. So you'd have to multiply it by y.
Agreed? And what will the plus x get you?
1.
Right. Is it looking less weird now and more like a process? That if you're wondering what on earth does this look like, because it's not really, you know how derivatives in Calc 1 were the slope of the tangent line, right? What does these things look like? Can you imagine a surface, right, in 3D space, right? So f of xy is the top of the hill, right, as it undulates up and down. If you draw a line parallel to the x-axis and slice it, don't you now get a curve? The derivative of that curve is in. And if you slice it parallel to the y-axis, you'll get the other fella, right? So visually a little bit harder to imagine, but essentially you take a surface and you slice it parallel to the x-axis or parallel to the y-axis, and what you're looking at is just a snapshot of the derivative in one of those orientations. Let's try the other fella and see what he looks like. Well, if you differentiate this one, you'll get 2x cubed y. If you differentiate this guy, you get x cosine of xy. And if you differentiate him, you get nothing. sometimes your function won't be written as f of xy. It'll be written as z equals. So if I wanted you to do the partial derivative with respect to x, I could use that notation or that notation. Are you comfortable how the notation adapts depending on what you're given or the way it's given? So let's see what this fella would look like, right? If you differentiate with respect to x, e to the xy, you get e to the xy. Do you get anything else?
Don't you have to have a y?
Yes. And if you differentiate this with respect to x, don't you just get a y cubed? And if you differentiate this with respect to x, you don't get anything. Now, if I go the other direction and do the partial derivative with respect to y, this fella will be e to the xy times the derivative of that, which gets you x. This fella will become 3xy squared, and that guy becomes nothing. And have you noticed that the two answers are, as expected now, different? Any questions so far? Really, what I'm wanting to get here is skill building, right? Just getting used to finding partial derivatives of eventually uglier and uglier functions. Let's put in some square roots. They tend to cause problems. Let's have, just because I want to, w is equal to the square root of x squared plus y squared. And we are going to find the partial derivative with respect to x. Now, if I want to differentiate this function, it makes a lot of sense to call it a half power. Because writing it that way, won't it make it a bit more obvious that it's a chain rule? So let's see what you get. You multiply by the power, and you reduce the power by 1. And then don't you finish with the derivative of what's inside the brackets? What is the derivative of x squared plus y squared?
Two x.
Okay. Now, this is the first time we've needed to do this, but is it expected? Style points, right? Make it look as pretty as it can. Right now, this answer is halfway. It ain't 100% finished. The half and the 2 cancel well. So I'm going to call that x. And this is a negative power. And I'm going to bring it downstairs. And I've got that. Is that finished, or can I make it look even prettier?
It can be prettier.
Okay. What will I rewrite the bottom as? How will I rewrite x squared plus y squared to the half?
Shouldn't it just be x plus y?
Bad. Danger, Will Robinson. Not a good idea. You're not allowed to
Square root?
separate. Yeah, square root. You can only simplify square roots if two things are multiplied. You can't simplify it if they're added, right? The rules for style points are factor the heck out of it and make it look like the original. And if trig's involved, look for some identities that might make it nicer. And that's basically the usual kind of rules, right? Factor the heck out of it. I'm assuming you collect like terms and so on, right? But factor the heck out of it and then make it look like the original. Now, I can tell you the answer to this without doing any work at all, but using this guy to help me. Anybody want to have a guess at what the answer will be, even although I'm not going to go through all this working?
Wouldn't it be y over the square root of x squared plus y squared?
Yes. You want to explain why? What made you think that?
Because they're added together, so they don't would like do the same thing, except instead of multiplying by 2x, you're multiplying by 2y.
Okay, so you're kind of figuring out what the question would look like if you did it in your head, which is fine. What I want to show you here is a little trick that you can sometimes use to make your life a little bit easier. Some functions, not many, but you know, when you meet them, you're happy, are called symmetric. A symmetric function is one in which the two variables could be switched and the equation would still be the same. Would you agree if I made the x a y and the y as an x, wouldn't that be the same expression? Right. That's an example of what we call a symmetric function. If you have a symmetric function, then the two partial derivatives won't be exactly the same, but they will be related. Whatever is an x becomes a y, and whatever is a y becomes an x. So do you see that that guy and that guy? Now I'm going to pretend I know the answer to this next question to show you what I'm getting at. And let's pretend that I had this as my function, and I'm making this up, but let's just pretend that we found the derivative and it ended up being this fella here. Just for argument's sake, right? I should be able to figure out what this guy is without doing a whole load of work. And trust me, wouldn't that be a quotient rule with a chain rule and a whole load of horrible algebra, right? So imagine we did it and it ended up being that, right? Just for argument's sake. What would the answer to this derivative be, assuming that you did this correctly? Using symmetry, essentially.
3y squared over the square root of x plus y cubed.
Can you see the symmetry helps us to do an answer, right, without actually going through the process? So if you ever see a function that is symmetric, and symmetric just means the x's and y's could switch places and it'd be the same guy. If you see that, you say, great. If they're going to ask me to find both partial derivatives, which most of the time they do, I'll only need to do a whole load of hard work to get one of them. And then once I've figured out what that is, I can figure out the other one without any extra work. Now, the only thing I ask you to do, if this was an exam, is that you say this little sentence. By symmetry. And if the minute you write that down, I'll say, oh, okay, you didn't cheat, you just used symmetry to do the second answer. Can you imagine that might help you if it's really ugly and it took you 15 minutes to get the first one? Do you really want to spend another 15 doing the second one? Or do you want to spend a few seconds just writing the answer down? Any questions so far? Is things looking good? Right, let's pick some questions from the homework. This is question 3. So we have a function and it's x to the 7 sine of y, and we're being asked to find that guy and that guy. Me personally, I would have just called it those two guys, but it's the same thing. Right, if you do a partial derivative with respect to x, you get that guy. And if you do a partial derivative with respect to y, you get that guy. Are we comfortable with that? It's a kind of one-liner, nothing too weird going on. Okay, let's see if I can find something more interesting. Okay, this is question 5. And we're being asked to find this guy and this guy. Okay. What is the derivative of this fraction with respect to u?
One over v to the 6th.
Agreed. Isn't it just like, I know, u over 20? Well, differentiate u over 20 is like a 20th, isn't it? You get 1 over 20. Now, if you want to do this fella with respect to v, I strongly suggest that you write it that way. Can you see that's going to help you do the chain, do the power rule? So what's the derivative of this guy with respect to v?
Negative 5u over to v6.
I think you changed your numbering. Negative 6u, v,
Oh.
and negative 7, right?
Yeah, that's what I meant.
Multiplied by the power and then reduced by 1. But that's not the guy we need. Don't you need that guy because of cell points? Make it look like the original. And you know, the original was a fraction, so make that a fraction. Oh, chain rule. Almost missed that one. So here we have a multivariate function. Something to the power of 7. I think when I see that, I'm thinking, hey, got chain rule. If you do it with respect to x, 7 lots of this guy to the power of 6, but then don't you finish with the derivative with respect to x of this guy, and that's 2x plus a y. And typically, this is just cosmetic, but you really should write things down in order of complexity. So that would be the final style point answer. Now, if you do this fella with respect to y, it's still a general. It's 7 lots of this guy to the power of 6 times, and the derivative of this with respect to y, that guy gets you nothing. And this guy with respect to y just gets you an x. That's all you get. And so it's 7x, x squared plus xy to the 6. Are we good? I hope sometime today, maybe already has happened. Are you looking at partial derivatives as just differentiation with a new rule?
I'm wondering if you can combine the two, the dx and the dy, and so you could get a combination function that describes the movement of both.
There is a partial derivative that might be what you're thinking of, where you do both. I don't want to do that today. I'll do that tomorrow. It might be what you're thinking. Okay, this is the last one. I'm beginning to regret it already, but I've committed to it, so I'm going to do it. This guy has got pretty much everything that could make it ugly happening. Have you noticed that it's got A, B, C, and D in it? Aren't A, B, C, and D considered constants all the time, no matter who the variable is? And then you've got a variable X and a variable Y, and they are going to change, switch places depending on which derivative is being asked. Now, I'm only going to do one of the two. Do you want the X or the Y? It really doesn't matter. Which one do you want me to do?
X.
Why?
X beat it by a few seconds. Now, what I see, and hopefully you see it as well, is don't you see a quotient rule? Right, it's a fraction. So it's going to be f dash g plus f of g dashed over g squared. Right, now the g squared is just the bottom being squared. Now f dashed and g dashed, whatever that happens to be, remember x is the variable. So if you differentiate the top, right, this guy here, with respect to x, do you see that you only get a? Right? Ax gets you a. What about the by? That's like b times 42. It's still a number. Its derivative is 0. So all you get out of f dashed is the a. You leave the bottom guy, the g, alone. Take away, you leave the top alone, which is that guy. Now, what do you get if you differentiate the bottom with respect to x? Right? G dashed, in other words. What do you get when you differentiate the bottom with respect to x?
C.
You get C. Do you think I am going to leave this as the final answer, or do you think we have some style points to do?
Style points?
Okay, what do you think? You're right. What do you think I should be doing then? What should I do to the numerator, the top?
Distribute the A and the C into the
Okay.
parentheses.
Right, so a times this is acx, a times that is ady, minus this guy gets you minus acx, minus this guy gets you minus bcy. Do you see anything nice happening here? On the top? Do you see anything nice?
The AC axis can cancel.
And so I now have ady take away bcy. Would you agree it's a little bit prettier than it was? Can we do any more? Factor the heck out of it and make it look like the original, okay? That's our basic rules. Anything I can do on the top?
I mean, you could factor out the y, but
Oh,
doesn't
you're
cancel or
thinking,
anything.
no. It does make it slightly prettier, so you should do it.